Welcome everyone to this talk and this stream today on MLOps and machine learning, DevOps for machine learning more or less. My name is Alexander Slotte. It's about 4 p.m. Eastern time here in Washington DC, and I'm more than happy to have you on this stream today, and we'll have some fun discussions and hopefully some new learnings as well. We are going to start off this talk by setting some basics on what MLOps is and what we can expect to learn as well, and then eventually we'll dive into a demo in Azure Machine Learning. We're using Azure DevOps and a real machine learning model and training, and see how we can get that all automated and nice. We are not going to talk about machine learning too much per se in this presentation, meaning that we won't focus on how we train a model so much, what tools we can use, how evaluation metrics work, and those kind of things. We're instead going to focus more on the machine learning workflow and the life cycle, and how we can get that automated and repeatable and just very robust to get things to production really quickly. The tools we're going to use today are, as I just mentioned, Azure Machine Learning and Azure DevOps. There are of course other open source tools out there that you can use, something like MLflow and other alternatives. So definitely don't think that these are the only ones. So to start off with, what is MLOps? Well, MLOps comes in many shapes and many names. I think you may have heard terms such as AIOps being laid out there in the community. Another very common term that is picking up pace is CD for ML, so continuous delivery for machine learning. Martin Fowler, for example, has written quite a few articles, and so are ThoughtWorks on this specific domain, and that completely makes sense. I generally like MLOps. I think it's fairly explanatory. What we are working on here is, of course, machine learning and operations, trying to see how we can operationalize a machine learning model quickly and efficiently in the same way as with DevOps. Another reason to pay attention to MLOps, or CD for ML as mentioned here, is that ThoughtWorks has put it on its tech radar as of I think November this year in trial mode, which means that it's something that we should definitely pay attention to, something they think that the industry is benefiting from and is worth looking into more thoroughly. And as I mentioned, a lot of us already, as software developers, have got a lot of benefits from DevOps when we're developing applications. Having that continuous integration, continuous delivery, continuous learning, from being able to push our code to our trunk-based development and straight into automated tests, maybe some exploratory tests by QA, but then go all the way to QA environments and eventually to production without too much human interference is fantastic. Taking full responsibility as an entire team on not only the code base but also how we deploy it is very important to succeed. And DevOps, as we all know, has allowed us to be much faster to production. We have teams at Excella here that deploy to production 100 times a day for any code change they're doing, which is fantastic, as we can really experiment on things so we can see changes in real time. It's like, for example, if you buy a bike or something else on Amazon or in a store, if you know it's been packaged and ready to go, you don't want to wait a month until it's delivered. And the same thing, of course, with software applications and software development. So why this sudden focus on MLOps? Well, just as software engineering and software development has matured over the years and realized that this is an issue and we need to tackle delivery as well, and not only development of application, so has the data science community. In many last couple of years, or when even since this started picking up speed, I guess, in early 2010s, data science and machine learning has kind of been a little bit of an ad hoc process, where data scientists focus more on trying to get a model that's working well, of course, which is the prime objective, and not focus so much on how to automate parts of the process, how to get it reliable, and how to get it faster into production, right? And so this whole shift to focus on MLOps is all about making sure we increase that productivity. And I think Bridging together the data science community and the software engineering community is very beneficial. As software engineers, we are very good at automating things. We're good writing scripts. We don't like repetition and so forth. So having that kind of cross-functional team can really bear some fruits here in terms of MLOps. Another thing to mention as well is that MLOps is difficult. Machine learning by itself is difficult, and so is operations. And I would even say and argue that it's slightly more difficult than DevOps is today. In regular DevOps for software applications, we primarily focus on our code base that we're trying to deploy, and then of course the deployment target that we're trying to get it to. And of course there's various techniques to do this, blue-green deployments, canary deployments, and so forth. I don't want to go into those details in this talk here. But with MLOps, as we will see later in this presentation, there are multiple dimensions of change. Not only do we have the code that may change, that can break things, but we can also have the data, we can have configuration changes and other things as well. I would even argue that time is a degree of change here as well. So that is definitely something that makes things a bit more difficult. So if we drill into it even further and look at why is it so difficult, let's take a look at normal production systems for software development. In general, those are auditable systems. We can easily see the logs, we can easily see the behavior, and we can understand what's going on, right? It's understandable, it's auditable. We can, from a functionality or a feature that is being put into production, we can track it all the way back through Jira or whatever source ticketing system you have, and look at the commits in GitHub or in TFS, and really kind of follow everything through and see who's done what and so forth. So it's very auditable. We also can test it thoroughly. We can put multiple layers of unit test, multiple layers of integration test, and functional tests and so forth, and the behavior is very reproducible and it's deterministic, right? Makes it pretty easy to work with, although of course code, as we all know, can be hazardous sometimes and will do mistakes. But that's mostly on us, not necessarily the code. It's deterministic, it will do the same thing every time given the same inputs. Machine learning, on the other hand, that we're trying to automate here, it's not necessarily deterministic, right? It can also be very hard to explain. We can have these black boxes for deep neural networks that takes inputs and makes a prediction, but we don't have any insight in how it came up to this decision. A good example of that, of course, is detecting faces. We know that it can detect a face, but we may not know what part of the face it's looking at to determine things. For example, it was trying to detect, I think, trying to distinguish between wolves and dogs in one model. And the way it was distinguishing between wolves and dogs was not necessarily any features in the dog or in the wolf. It was the background in which the animal was portrayed in. So if it was a wolf, it usually had more snow or more forest, those things behind the scenes. While in the dog, the picture couldn't be taken in the kitchen. So understanding how it thinks is pretty important, but it's also very difficult. It can also be very hard to test these machine learning models, and we'll definitely dive into ways we can simplify this. And it's also very hard to improve because we have to have a baseline, we have to understand what is a good model, what is a bad model, and that ends up being a lot more difficult than in normal application systems. So in this presentation, I do want to try to give you the answer to what MLOps is trying to address early in this presentation, and then I want to walk you through some things to understand why these are issues and how we can, and what some challenges are with those and ways we can solve them. So the four things that I think MLOps is really trying to address is model reproducibility and versioning, auditability, explainability, packaging, validation, deployment, and monitoring. So with that said, there's a lot of fancy words here, but what we're trying to achieve here is we're trying to make the machine learning process fast and iterative so that we can quickly improve and try new models and put it in production very fast. Why do we want to do that? Well, we may want to experiment with the model in production, and we can't wait for 2 months until it's fully automated and fully validated. We may want to put something out earlier and see how it behaves. We also may work in we also have auditability requirements. For example, if we work in a government setting or a federal setting, we may have requirements on ourselves to also explain how a model makes a decision to ensure we have fairness and bias in all these things as well. If you have a live stream of video, for example, and you're doing predictions on real-time video, we want to ensure that our latency requirements are being met here, so we can get real-time predictions. How do we do that in a safe way and a smart way, so it can be fully reproduced on anyone's machine? All of these things, as we'll see, can usually be done locally, but as teams grow bigger and we have more cross-functional teams, we want to make sure everything can be run not only on your local machine, but also on a build server or in some other setting. So to kind of drill down into some of the details here and to understand how these challenges come about, I want to discuss the machine learning lifecycle with you to showcase some of the most common steps that happens when you train a model. So there are many different representations of this lifecycle and this process, and by no means is this the only one, but I think if you look around a bit, you will see some of these common themes here. The four kind of pillars I want to discuss is the data step, the modeling step, deployment step, as well as the monitoring step. And it's a circle, of course, because this is a reiterative process, and we'll go back and forth and do it over and over again. But in general, the business or organization that you're working for will come in with a business need, something they want to get solved. For example, they may want to create a recommendation system to have products recommended for you that are close to what you previously bought. So think Amazon, or think Netflix if you're looking at videos. They may want to create a fraud classifier system if you are a bank or something like that. So you'll usually come in with a business need. The first thing that will happen in this process is that we need to figure out where the data is. We need to acquire some data, we need to wrangle it a bit, explore it, clean it, transform it, those kind of things. The data normally comes from transactional data systems, but it can easily come from flat files as well, like Excel files or CSV file, or they can come from data lakes, which is becoming more and more popular. Depending on how large our organization is, this step can usually be handled by a data engineer that builds ETL systems and data pipelines, but it can also be handled by data science directly if the system or organization is not so big. It really depends on scale here. What we're trying to do here, though, is we're taking raw data from multiple sources, we're combining it in some kind of way that makes sense to us, and we're making sure it's clean and pretty enough for a machine learning model to make sense of it, which means that we want to get rid of all the missing values, we want to get rid of all the outliers and so forth, and we want to also pivot it in such a way that it makes sense for a model, meaning that we don't want any text or those kind of things in there. The following steps then is to model our machine learning model. So we're taking our data that we have processed and got to a nice shape, and we are looking at the features in that data set. We may be adding features, we may be removing features, we may be deciding that some are completely irrelevant, right? For example, if we look at the fraud classifier case, sometimes the account that we're going to, the amount that being transferred may be of interest, but you may want to combine features such as the amount being transferred plus the amount that was on the account being withdrawn from plus the amount on the account it's going to. That combination of features may actually make more sense for a model and have more predictive power. So we may use feature engineering there to find other kind of fun solutions. In general, this step is usually done by a data scientist or a machine learning engineer or something like that, depending on what you call it in your organization. And we take our process data and we put it into, we train it and evaluate it, and out we get is as a machine learning model. Important to note as well is in this step, we are also evaluating the model to see how good it is. So we're getting metrics. Metrics can be accuracy, it can be F1 score, and those kind of things, depending on what kind of machine learning problem we're trying to solve. But in general, we're getting an output here on how good the model is in some way or another. But once we have a good model, we got a nice shiny model, we need to put it in use. It doesn't do any good on a local computer, it doesn't do any good on a shelf, so we need to put it in use. There are many ways of putting it into use, putting it into deployment. One common model is, of course, to put it into a Docker image, expose it as a web service in a Kubernetes cluster, and let a software application integrate to that model by just simple HTTP calls. Another way of doing this is to embed it into your application. For example, I work a lot with a machine learning framework called MLOps in C#. So what that allows me to do is to call my machine learning model as a function straight from my web application or from my mobile app. There's some similar concept as well in the Python world that you can write SDKs for it, but the essence is that you can embed your model into the application so you don't need an outgoing call. This is of course good if you want very short latency, and that's one of your requirements. You don't want HTTP requests or what have you. But of course, it also means that you need to deploy the application together with your machine learning model. So it kind of depends on the use case. Regardless though, in this deployment step here, usually you have a software developer or machine learning model that works together with operations to try to figure out how we can deploy and consume the model in your application. Because in the end, a machine learning model rarely is useful just as a web service. We usually want to embed it in some kind of experience, a user experience, recommendation system, or something else, right? But depending on how large the team is, we may have different actors involved here. The final step in the lifecycle, as we saw, is the monitoring step. So just deploying a model to production doesn't necessarily give us any benefit. Well, of course it does, but we can't just leave it out there in the wild by itself. It's not necessarily just as an application where we usually see some kind of robustness in the system. A machine learning model decays over time. So some things we need to monitor here are predictions. So we want to monitor what kind of recommendations the model is doing, for example. We want to model bias and fairness to ensure that some groups in society are not getting neglected in some ways. There's no prejudice here. That can be for race or gender or something else. We also want to monitor drift from a baseline data set here to ensure that our application is not decaying just because of the data. A good example here, for example, is that if we're doing fraud detection and we are labeling transactions like fraudulent or not fraudulent, and if we then using the same data set again to train our model that has been enriched with additional data sets, we eventually will get, most likely we'll get a class distortion here, where we have more non-fraudulent cases than fraudulent, which eventually will mean that the model will be worse and worse at predicting fraudulent transactions. So that's one way of getting a drift, but there's also other ways of getting a drift of the predictions. Generally, depending on the size of the organization, we have many actors here that may want to stake in this monitoring part here. It could be operations, it could be app developer, but it can also be a data scientist. But we get out insights from this step. All right, and of course, this is an iterative process, so we go round and round in the wheel here. We may decide from the training step from the modeling step that we want to go back to the data step. We may decide from the deployment step that something is not working with our integrations. We want to go back to the data or the modeling step and so forth. Or we may go the whole wheel around and start over after we deployed it to make sure that we continuously improve it, right? So what are some challenges with this current approach where we have things kind of siloed? We have multiple actors and things are done mostly local on your own computer. Well, first of all, the most obvious one is that we have multiple sources of change. Each step has their own source of change, more or less, right? We have the data step where data can change. We have the modeling step where configuration and the code can change. We have the deployment step where configuration definitely can change, how we deploy it, or contract changes on prediction APIs, and so forth. So multiple sources of change here. Model versioning and data versioning are not equal to code versioning either. That's something that's important to note. Especially data versioning is not equal to code versioning. So for example, how can we know which data was used to train a model on? How do we know what the pre-processed or the processed data looked like? Do we take snapshots? Do we put them in GitHub? Not sure. Or do we don't do it at all? Some cases it's not feasible, others it's feasible, and something we should look at. Same thing with model versioning. It's not necessarily a good idea to put the model into GitHub. How do we how can we have different versions of the same machine learning model? How can we experiment with some of these things? As I already kind of alluded to here as well, how do we create this digital audit trail? Once we have a machine learning model in production, how can we trace it back all the way to which code was used, which data was used, and which configuration was used when deploying it? How do we get that audit trail? And that's especially important for regulated industries. As we mentioned as well, model decays over time. How do we approach these things? That could be, the time is in production is going to change. That could be because we're getting new products into our product catalog and our recommendation system does not know about them, not trained on that kind of data, so we will not recommend them. So that's the way of model decaying over time. How do we handle the work of my machine syndrome here, right? We have data engineers working on the pipelines on their own computers, maybe transporting flat files to a data scientist doing their own things on their own machine, and so forth. How do we address that? And finally, how do we know if the model performs better than the previous one? How do we easily get access to the metrics of the model current in production? We don't necessarily have that issue with application development, because we just know if our unit test passes and things looks good, we put it into production, it's a new feature. We rarely change the same feature again, right? But here we actually changed in the same model over and over again, and we want to make sure we are improving it in every facet. So how do we keep track of that? Well, let's take a look at each one of these challenges more in detail, and let's start with the dimensions of change here. I think most of you have already figured out that some of the dimensions of change here is the code, the model, and the data. How can these change, and what are some reasons for these to change? Well, if we look at the code itself, the one obvious one, of course, is new features. Our application can get a new feature. We can get something that will require a model change. We can also have bug fixes or configuration changes in our code that will trigger the need to do something new. This could both be in our application code, but it can also be in the code that we use to train our model on, right? For example, we can get new requirements here for performance, new requirements for latency, and so forth. One of the biggest sources of change here is the model. If we get new data, new incoming data, we definitely need to train the model because the data will definitely affect the outcomes and the robustness of the model. We may decide that we need new dependencies. So what do I mean with dependencies? Well, let's say we're using TensorFlow to train our deep neural networks, but then we decide that we want to use PyTorch instead. That's a new dependency. That can definitely change the performance of the model. Or maybe using pandas and NumPy, or we're going straight over to using MLOps in C#. So dependencies here can definitely affect things. Performance of the model again, what the performance is, what the CPU load required is going to be, the memory footprint, those kind of things and those requirement changes can definitely trigger that we need to train a new model. The most important one is the first one, which is research. So what do I mean with research? Well, machine learning or the data science kind of paradigm here is very experimental. It's not necessarily as structured as software engineering. You may not fully know if a model is going to perform better than another model until you actually tried it. You may change an algorithm, you may change hyperparameters going into an algorithm, you may fine-tune something else, and that may or may not improve the performance of the model. So what's the recommended approach when working with machine learning and MLOps is to have feature branches instead for each permutation of your experimentation, and having a CI build trigger of that going through the whole flow to see if it's better or not than the current model in production. And I know that completely goes against a lot of the trunk-based development philosophy that's out there right now, and there are some good reasons why it's doing that. First of all, the trunk-based the development style is very useful for a couple of reasons. One, because you normally every you want to avoid feature branches in general, because generally they all get merged to the same branch. Also, you want to avoid long-lived branches and so forth. In the machine learning world, a lot of these feature branches will never be merged into the trunk-based master here, right? Because they may usually not be better than the model in production. So we may have 1 out of 100 branches being merged into the main branch. So that's one of the considerations as well. Also, we are not going to see as many merge conflicts as we will do in software application and software development, because the changes to the code that trains the model are usually very small. It could be just with one parameter. It could be changing one value from 3 to 4 or something like that. It's not going to be multiple files and multiple changes. So those are some reasons why you usually want feature branches to experiment and do some research. The third degree of change here that will trigger a new model to be built is data changes. We can have schema changes in our data. We can have new columns or new relationships that will affect how we structure our data. So the data pipelining step here, the data engineering step, may have to change, causing all the subsequent steps to change. We may have a change in sampling frequency of our data. So for example, we may have weather data that we're using to make predictions, but if the sampling of the weather data changes, that may change our predictive power as well on how many cycles we can predict in the future. The distribution of data can change. Again, this is very important. For example, fraud systems. If the distribution between fraudulent and non-fraudulent transactions changes, that can definitely sway the model to favor one over the other if we're not careful. So if that distribution changes, we want to ensure that we train a model again. We make sure that we have all the tests in place to ensure an accurate model. Cardinality, of course, that's something that comes into play for recommendation systems. If you have a product recommendation system and the model is not aware of the new product that you just released, it's not going to recommend it because it's not trained to know that the model is like. So if the cardinality in, for example, a product group is changing, that will also trigger the need to retrain your model. All right, so that's some of the axis of changes or dimensional changes and one of the challenges. If we then move on over to the last step here of those challenges, how do we know if the model performs better than the one currently in production? What are some ways we can test machine learning models and fully automate that? Martin Fowler has created a really nice pyramid here that I definitely want to walk you through as well. And it's a way of rethinking the regular testing pyramid that I'm sure you're familiar with when it comes to automated testing, where we have AUTs and functional tests on the top, and then as we go down into the foundation of the pyramid, we're going closer and closer to unit tests and fast tests. Martin Fowler proposes pyramids within pyramids, more or less. So at the top here, you see some of those normal concepts from software development with exploratory testing, end-to-end testing, integration testing, but at the end here, we are changing up our testing layers and adding multiple facets here. To the right, we have those more common tests that we're aware of, like unit tests and service tests and contract tests. But then to the left, we are merging into more of the machine learning space here in the data space. So we want to test things such as the data pipeline, right? If the data step is such a big part of our machine learning lifecycle, we want to make sure that the data coming into our modeling step is sanitized. It has the proper missing. I mean, if the missing values is one thing that we're trying to clean up, we want to ensure that it doesn't have any missing values. We want to ensure that the cardinality in columns are correct. We want to make sure that our transformations and feature engineering is correct, and so forth. So we can have all these tests just to validate the data we train the model on is at least in a good state. Then we can go into the machine learning pipeline and we can look at unit tests for that specific area. And what do I mean with that? Well, we can have tests to ensure that the accuracy of the model is not degrading, or that recall and precision for a fraud detection system is still at a reasonable level. So we can have those kind of tests just to make sure that the model is actually performing better than the current one in production. And to add to that as well, we want to have different facet tests for bias and fairness to ensure that if we just look at this specific group of our data, it's not getting favored or disfavored in any way. And of course, we also have to look at model performance to ensure that the prediction speed, or the speed of predictions, I guess, is within reasonable limits from what the business expects. So from this slide, I just wanted to take away some learnings here, that there are many ways to test a machine learning system. In general, it's a little bit more complicated than a normal application, but it's completely possible. You just have to think about each part by itself. All right, so let's look at monitoring. Monitoring is the last step of our machine learning lifecycle. What are some things that we want to monitor, and what are some challenges with a model decaying over time? So I will group monitoring usually into two buckets. We have internal monitoring and we have external monitoring. Internal monitoring for me are things that we're used to as software developers, looking at exceptions and warnings, errors in our logs to ensure that things are working as expected. Maybe looking at latency for web requests or other kind of requests within the system to ensure that it performs well, and so forth. And there's tons of things to add to this, of course, but more or less I see it as a bucket that the system is in a good state. Then we have external monitoring, which I entitle more to the machine learning world and domain here, where we're looking at how the model is really doing by itself. There's kind of three buckets I want to talk about, which is monitoring model inputs, outputs, and fairness / bias. The model input, of course, is what kind of data is the model receiving to make predictions on. So why is this important? Well, if we train the model on certain inputs, so for example, the cardinality of a specific feature or a field in the incoming data, we also want to ensure that it does not get unseen data or permutations that has been trained on, because we maybe not be aware of what the predictions may be then. So we want to ensure that whatever the model is seeing is something it's used to, and if it's not, then we may want to trigger retrain on new data. At the same time, we also want to see what output is, and output is the predictions that the model is creating. Are the predictions as expected? Are they meeting KPIs of the business? For example, are we actually recommending products that make sense for the user currently logged in? Are we actually finding transactions that are fraudulent in the fraud system, and so forth? So we have to look at those outputs and those predictions. And finally, we also need to monitor the fairness of the application. So we can't only run unit tests for this in isolation before putting in production. We also need to run tests and monitor these things while it's in production. We can't leave a model in the wild. And any of these things may or may not want to trigger an automated retrain process. So you've seen all the challenges. You've seen a lot of the machine learning lifecycle and how we go about things. So what do we need to succeed as data scientists or as software engineers to fully automate the machine learning process and really kind of embrace MLOps to bring machine learning models to production quickly and safely? Well, there are a couple of things I do want to highlight and discuss here. The first one here is discoverability and accessible data. If our data is easy for data scientists to access and to work with and to play around with, we're going to get better models, and most likely the models are going to use features that makes more sense. If we have some way of version controlling both our data pipeline, our code that we use to train our models on, as well as versioning our models, we'll get a lot better results as well, right? We also need a quick and easy way to continuously deliver new models to both a testing environment as well as a production environment. And just the same way as we're doing that for software applications. We don't want too much human intervention here, although we definitely could use some manual gates here just to approve it for production. And that makes sense to make sure that nothing wrong is going out. We also need infrastructure for running multiple experiments. So if you go back to the slide when I was talking about research, we may have multiple data scientists or one data scientist that are running multiple experiments in parallel because they want to try this algorithm and these hyperparameters for the same model to see which one is best, and then pick the one that they like the most. So we can't necessarily run all of the things locally, or neither maybe want to, depending on how the compute cost is. So we need some kind of cloud infrastructure to run multiple experiments in parallel and also keep track of what each of them are and what the results are. And again, we also need some way of tracking the performance of the model, seeing which one, how good the one in production is, so we can easily compare that with one that we're currently training. And finally, as we just talked about, we need some way of monitoring our model in production. Alright, so that's a lot of information to you guys. Thank you for listening so far. At this part of this presentation and this discussion here, I want to switch over to ways we can solve this, some tools out there to really help in the MLOps process to automate part or fully this workflow. And we're going to talk about Azure Machine Learning and Azure DevOps in this presentation primarily. What we're trying to achieve here is we're trying to achieve a greater understanding and greater degree of collaboration between an app developer as well as a data scientist trying to create a model. And this collaboration can happen in GitHub, and based on the commits or branches that are committing there, we may want to trigger an Azure pipeline, running unit test on the machine learning model, data validation test on the machine learning model, and then eventually publishing a training pipeline to a service called Azure Machine Learning that will go into more depth later. This pipeline and this service in Azure can then evaluate the performance of the model and register a new model if it's deemed good enough. And it can also manage a lot of things such as deploying it to production or a test environment and monitor the application once it's live. A good slide to kind of elaborate on this is this slide here, which is taken directly from a repo of sample code that Microsoft provides. There's a couple of buckets here that I want to highlight. The first one we definitely should talk about here is Azure DevOps build pipeline bucket, right? So imagine a data scientist doing a change in the code that trains the model, right? He or she checks that into a branch, and that triggers a CI pipeline in Azure DevOps. That pipeline can do a lot of fun stuff, but one of the things we definitely want to ensure is that it's doing code quality checks, so linting, for example. You can do data sanity checks to ensure that the data that we are training the model on is sane. It can do unit tests on the machine learning, the model code as well to make sure it looks good. And what it also should do is building this training pipeline using an Azure Machine Learning SDK. And we'll dive into that just a bit. Once that all those unit tests has passed, we can then push that training pipeline to Azure Machine Learning, which is a cloud service, right? In general, that pipeline will have 3 steps. Usually those are Python script tests, because right now we only Azure Machine Learning only supports R and Python. Hopefully it supports C# soon. But it'll be 3 steps. It'll be train, evaluate, and register the model. And usually the registration step is optional, depending on if the model is good enough. There's no real need to register a model in Artifactory if it's worse than the current production model. So that may be a conditional step that we may want. This training pipeline can be triggered by multiple things. It can be triggered by schedule, or it can be triggered by data changing, but it can also be triggered by the fact that the CI build wants to just train a new model. So if you zoom into the Azure Machine Learning step here and kind of look at what the training pipeline is going to be built up, it's going to be built up by, usually it's going to be built up by a Python script that creates the training pipeline. And the training pipeline is going to be constructed of 3 steps. Each step is usually going to point to a script file that does a specific thing. So for example, we may have a training script, an evaluation script, and a registration script of the model, right? The training pipeline script by itself that we're pushing to Azure Machine Learning, it's let's see if I lost the words here, is using an SDK for the Azure Machine Learning workspace. So by using that SDK, we can get the clusters that we want to train the model against, we can get the workspace that we want to register the model in, and so forth. So pretty cool, easy stuff here. But what I want to highlight here is that all this code here, the training pipeline code, the Python script for training and evaluating model, they can all be sourced in GitHub and stored there. And then based on a commit, we can build all those things in Azure DevOps to ensure that everything looks good. And then we can execute the training in Azure Machine Learning. I hope this slide gives you some clarity in that, because for me in the beginning it was a little bit ambiguous on where things are executed. So I think this slide at least helps to explain some of these concepts and what we're actually doing here. All right, so once we have trained our model and things look good, and the model is actually better than the one we have in production, what we do is we're putting it, we can decide then to deploy it to a QA environment or to production using Azure DevOps as well. And normally we can do that in, we can deploy it for testing in Azure Container Instance, and we can deploy it in production in a Kubernetes cluster if that's the way we want to serve the model. All these compute targets and all these clusters can easily be handled through the Azure Machine Learning servers. So that's not necessarily part of Azure DevOps, of course, but the deployment and release can be done through Azure DevOps, just as we do normal deployment for software applications. All right. So some resources that are very useful is one blog post by ThoughtWorks and Martin Fowler. And then Microsoft as well has a lot of good documentation on MLOps in general, but also more detailed on Azure Machine Learning. So I strongly recommend you take a look at these if you're interested in learning more of the concepts and ideas here. All right. So I definitely think we have enough slides. Thank you for bearing with me so far. You've been great listeners. And I want to dive into more of a demo now and see how this is actually done in real time. So to do so, we can switch over to Visual Studio Code. And also, by the way, if you have any questions on what I've talked about so far, or just in general, feel free to chat to me on Twitter or anything else, LinkedIn, whatever medium you feel necessary, and I'm happy to answer any questions I can. All right, so what we're going to do now is that we're going to look at a simple example to train a machine learning model on diabetes data to predict if someone has diabetes or not, more or less. The data is not so important. It looks like this, nicely colored, right? We have different columns for different things here. And I think this data is normalized in some way because it's age doesn't make any sense. But we have data anyway to train our model on. And again, the machine learning problem itself is not so important here. But what we do have here in this repository, as you will see here, is that we have scripts for different parts of the process. Let's see if we zoom in here to the left here. We have a script again to train a model on, right? We have a script to register a model and a script to evaluate a model. And usually, again, those things are kept in isolation. We also here have, I think it's under, data tests here. We also have different scripts here for our unit test. So we have data tests and we have code tests for a machine learning model. These tests here are doing a lot of funny stuff here. Like for example, we can have a unit test for checking missing values right here. We can have a unit test to check distribution again, right? To make sure that we don't have any biased data. And we can also have a unit test to check that our schema for our data that we're training our model on is sane. So those are all good unit tests to do before we even train the model. In addition, we also have a large script here to train to build our training pipeline. So remember, this is a training pipeline that we're going to publish to Azure Machine Learning that's going to contain each script step. So train, evaluate, and register. And we can see here that we are using the SDK for Azure Machine Learning here to get things such as the compute targets. So for example, that could be a training cluster using different credentials we have. We can also see here that we are using this to get a run config to determine which dependencies we need, such as NumPy and pandas and so forth. If we look at this script more in detail, we will see that we have steps here that we are familiar with. We're creating Python script steps here, and we are defining the paths to our training script, evaluation script, and our registration script here. And we're also passing in things such as build ID and model name. All right. So as you can already understand now, this is pretty well set up for creating a YAML file in Azure DevOps to do this fully automated. And that's exactly what we're doing. If we look in Azure DevOps here, we can see that we can create a CI pipeline, just like we do in a normal development setting. This CI pipeline and this YAML file is fairly complicated, so I'm not going to dig into the details here more specifically. And the example is online if you want to have a look yourself. But in general, there are multiple steps here for running unit tests, for running code sanity checks, and for building our training pipeline that we eventually, push to Azure Machine Learning. And we do all of those things with an extension in Azure DevOps for Azure Machine Learning. So if you want to do this, you need to install that into your workspace. But if we look at one of these builds here, we can see what it's doing more in detail. We can see here that it's doing those quality checks, right, and making sure they pass. We're running some unit tests. We're doing some linting and making sure that it works. And eventually we are creating that build pipeline and pushing it to Azure Machine Learning. So if any of these unit tests fail, or the data that we're trying to train a model on is not actually working, we'll get unit tests failing just like we do in normal application development, which I think is really, really cool. And since we can have these builds triggered on different branches that we do, like feature branches, we can have one of these CI pipelines being triggered when you want to do permutation of a hyperparameter or machine learning algorithm. And you can see how that change is executed and run in Azure DevOps and Azure Machine Learning and get the results nicely noted for you and documented, so you can go back to them and look at that later if you have any questions on what you tried so far. So this model here, it is running and it's pushing it to Azure Machine Learning. What it's going to do here is going to create a training pipeline in Azure Machine Learning, and it's going to invoke the pipeline to do a lot of fun stuff, such as training and validating the model. And that's a good segue to go into the Azure Machine Learning service and see how it looks like. So for some of you, it may be the first time you're in here. Azure Machine Learning is currently in preview. It was previously called Azure Machine Learning Service, and is now renamed to Azure Machine Learning. It's kind of the follow-up service from Azure Machine Learning Studio, which I personally didn't like too much. But it has some really cool features here, where you can keep your data sets. You can keep track of your experiments. So experiments, think of those as your different runs. So each feature branch will be an experiment, for example. Your pipelines, so those going to contain your train and evaluation steps and so forth, which models you registered, and what kind of endpoints you have both in your training clusters but also in production. And you can also manage things such as compute targets here, depending on how powerful you want your inference clusters to be. So for us, we only have one experiment because we only have one branch. And we can see here that we have last run it a couple of days ago. And with an experiment, we have multiple pipelines. So for each time we do a CI build, we are going to trigger a pipeline that is getting published, right? You see here that it was 10 days ago since I did my last push here, my last CI build, and it took 12 minutes to run in our cluster. But we get some really nice things here, because we know when we ran all these things, we know how long it ran, and we know who submitted it, and we get all these kind of fun tags here that you can add yourself in your Python scripts that get published. So domains and pipeline ID, things that you have in Azure DevOps to keep your auditability, those kind of fun things. If we look at one run, we'll see here that we get a representation of those steps that we had in our training pipeline. We have our training step, we have our evaluation step, and we have our registration step here. And each of these steps here, they correspond to that script that we use to run our model on. And if you click on one of these steps here, we can get a lot of details. We can get some logs actually from Azure Machine Learning when I was running it, as well as other fun things. And I believe we also get some parameters here. Yep, exactly. So we get some parameters here that was passed into the step, and those can be super useful for auditability. For example, we'll get a build ID here, right? And if you see here, in our Python step here, we are passing in the build ID and the model name here into each step. And those are things that we are going to be able to see here when we audit this. So these are really cool things. And I think the build ID corresponds to the one here in Azure DevOps. Maybe incorrect, but let me double check. That'd be really cool at least. I don't know where I see build ID honestly right now, so I'm gonna skip that. But yeah, some really cool things here, and allows you to get a good understanding of what's happening. So once we have run this whole pipeline, if the model is good enough and is better in production, we're actually going to register a model here in our Artifactory. You can do it yourself if you wanted to by providing the model more or less and anything else that you need to provide. But you can see here that we have tons of options here actually. But you can also do this automatically through the SDK to Azure Machine Learning. And you get all these nice things that you can see here. You can see which build it came from again, which run it was used, and so forth. And all the things that can allow you to trace back on the source data as well as the source code and those things that cause this to happen. And once you have your data, your model registered, you can actually go ahead and deploy it to an endpoint. And you can either do that through this interface if you wanted to. It's actually pretty simple. You can just hit deploy here, and you can decide your compute target and your compute name. I think we have an Azure instance, but we don't have a cluster yet. So you can deploy all these things yourself, but you need to provide all the entry files and the conda files here for that. In our example, we are actually deploying it through Azure DevOps instead. So we can set up a really nice pipeline here where we can deploy releases as we please. So for example, we can create a new release, or we can look at the one we already done here. And this nice extension to Azure Machine Learning will have an idea of this model here. So this call is sklearn regression 3, right? And if you look at the model in Azure Machine Learning, we'll see that we should have a corresponding model here, right? sklearn regression model version 3, right? And it knows about that one, and if we want to deploy it to Azure Container Instance or an Azure Kubernetes cluster, we can do so by just a click of a button. I think right now I have some issues with my container instance, so I can't do that. But in theory, it's very easy to promote things here, just like you do with software. And you can put gated stages here as well, of course, to ensure that things are only deployed when you really want them deployed. And finally here, there are ways to handle your training clusters, inference clusters, and so forth. Just as anything else in Azure is easy to create and easy to succeed. Nice. Well, that's kind of what I wanted to show you with a demo. I want to highlight that there are a lot of examples out there. So if you're interested in just trying this yourself, there is a great repo from Microsoft called MLOps Python that you can clone or fork. You can set up this environment really easily yourself. There are ARM templates for Azure to set up all the resources. So you can kind of get a feel on it yourself. I will say there's a lot of steps here to understand, especially if you're not a Python developer as I am. I'm more of a C# developer. But once you dig into the details, they make sense to you. They're just very verbose, I think. But once you look into the details, it's not much of an issue. So with that, I would like to say thank you for listening into this stream today. I very much appreciate your time. If you have any questions, again, reach out to me on Twitter or look at some of my repos I have on GitHub, and hopefully they will provide some answers to your questions. Thank you very much, and I hope you have a great rest of your day.